Hello everyone, welcome to the channel with YouTube. In this video, we'll see the demonstration of design and simulation of PMDC, that is Permanent Magnet DC Motor, using ANSYS Maxwell Software, that is RMXprt tool. In case if you have not subscribed to this channel, please do subscribe so that you will get the updates of latest videos uploaded under this channel. So before starting the today's session, just those who are new to this channel, I request all of you to go through the video uploaded under this channel only regarding introduction to the ANSYS Maxwell Software RMXprt tool. So while making the design and simulation of PMDC motor, you need to go through the few general steps. First one, insert RMXprt design and select the type of machine. Second, select the type of machine, that is PMDC motor, as per the design requirement. Then third one, rename the project as per your convenience. Fourth step, provide the inputs needed to design the geometry of selected motor, that is PMDC motor in this case. Fifth step, add the solution setup. Sixth step, analyze all. Seventh step, validate the design, and if there is any error, rectify that error. Then 8th step, right click on the setup and open the design sheet. And last step, the download design sheet. So without wasting the time, we'll start the demonstration. So when we open the RMXprt Simpler software, at that time we will get this GUI. So here, first of all, as we have discussed the general steps, you need to go through the insert RMXprt design. Then you will get the list of different machines which we can simulate by using ANSYS Maxwell RMXprt tool, like adjust speed synchronous machine, then BLDC motor, clock pole alternator DC machine, then generic rotating machine, single phase induction motor, PMDC motor, 3-phase induction motor, then 3-phase synchronous machine, universal motor, etc. But here, as we are going to demonstrate the PMDC motor, you need to select the PMDC motor and then you need to enter the OK. So when we enter OK, then you will get this new design sheet which is added in the project manager list. So here, if we click on this plus button, we will get the different sub menus. Okay, so according to that, you need to follow the procedure. But for the demonstration purpose, I have already selected this permanent magnet DC motor. So once you open this project, then as per your requirement, you can rename the project. So here just you can click the rename option and you can rename your project. Then what is the next step? You need to give the input data as per the selected motor. Like right now, we have selected the PMDC motor. So accordingly, you need to give the inputs which are needed to make the geometry of PMDC motor. So for that purpose, what we'll do, first we'll double click on this machine option. So once we double click, then you will get this window. So what is the information is given here? The machine type. So machine type is by default permanent magnet DC motor because we have selected this motor only. Then number of poles. So here we have selected the number of poles 2. If you are having any doubt regarding the information or the input information which is asked here, so for that purpose you can go through the description tab also. So what is the meaning of number of poles? Number of poles of the machine. So here we have selected 2 number of poles. Then frictional loss. So initially you can decide the losses according to which your machine will be designed or simulated. So frictional loss. What is the meaning of frictional loss? The frictional loss measured at the reference speed. So right now here I have assumed it is 0. Then windage loss means the windage loss measured at the reference speed. Then a reference speed, that is a reference speed at which the friction and weightage losses are measured. So here we have selected the reference speed as, or we have given the input, that is the reference speed is 2400 rpm. So accordingly we need to provide the input for to complete the geometry of this machine. Okay. Regarding the unit, if you click here, then right now these losses are in watts only, whereas in case of the rpm you can select the any one unit to give the input for reference speed. That means under the unit tab you can select the any one unit and accordingly you can give the input parameter information. Okay, once we input this value, then right now suppose here we have selected the 2400 rpm, then you need to press the enter the apply button and then enter OK. So we have given the general information of the machine, but under this machine, according to the construction of the permanent magnet DC motor, like permanent magnet DC motor is having different subparts like stator. Then in case of the stator there is stator pole, then rotor. Then in case of the rotor you need to give the information about the winding, commutator, then shafts. Then only the entire geometry of the PMDC motor will get completed. So now we have just press the plus button here, so we will get the sub menus. So first of all we'll go to the stator, so I will just double click on the stator, then it will ask the information or input for information of different parameters to make the geometry of stator, like outer diameter, inner diameter, length, stacking factor, grip steel type, that is material which is used to make the stator. So here outer diameter, as we have already discussed, if you want the more details about this parameter, you need to go to the description tab. So what is the meaning of outer diameter? Outer diameter of the stator core. So here I have given the input as 79 mm. Okay. Then inner diameter. So here in case of the inner diameter, what is the meaning of inner diameter? So inner diameter of the stator core, I have selected the inner diameter as 56 mm. Then I again inform you, I again give the information as per your design requirement. You can give the input for the different parameters. So for the demonstration purpose, I have already given the values and I am just giving the information. But if you are working on the particular research, or if you are going to work or you want to simulate the motor as per your design, just change those values. Then length, what is the meaning of length? Length of the stator core, here length of the stator core is given 100 mm. Then stacking factor, so what is the meaning of stacking factor? Stacking factor of the stator core, so here stacking factor of the stator core is 1. Then steel type, so what is the beauty of this RMXprt tool? Here you can select the different materials to make the different parts of the motor, and accordingly you can also check the performance of the motor before making the hardware model. So in case of the steel type, suppose I double click on the steel type. Right now here we have selected the material M19_24G, but if you double click on it, you will get the material library. So those who want to do the research by changing the different material, or by changing the material which is used to make the stator, rotor, etc., then you can select the different materials from the library, and after the simulation result you can decide the material which is best one to prepare the hardware model. Okay, so here in case of the material library, you can see there is a list of different materials. You can select the any material and accordingly you can check the performance of the material. But apart from that, if anyone want to work on the research related to the development of new material to enhance the performance of the motor, you can select you can add the new material which is developed by you under this library. For that you are having the options like view or edit material. Through the add material tab you can add the different material, then you can clone the material, you can remove the material from the library, then you can export to the library. But make sure that if you want to add any new material in this library, then you need to give the information of the new material in terms of this like name, location, origin, type, then relative permeability of that material, bulk conductivity, magnetic coercivity of the material, core loss, thermal conductivity, mass density, specific heat. And if you are having this information, just you need to click on the add material and you can give the information and you can add the material in this library. Okay, so this is the use of this adding the material library. But for this demonstration we have selected the M29_24G material. Okay, then next part is pole. So in case of the pole you need to give the inputs like imbalance, offset, magnet type, magnet length, then magnet thickness. So first of all, pole imbalance. So here we have selected the pole imbalance 0.726. Then offset is 0 mm. What is the meaning of offset? So as we have discussed, you can go through the description tab like pole arc center offset from the center rotor core, rotor center. Here and 0 for a uniform air gap. So here we have considered the uniform air gap, and that's why offset is 0 mm. Then magnet type. Here you can select the different magnetic material. This is also another one research area. You can select the different magnetic material among the available material list and you can check the performance, and by comparing the performance of the motor for a different magnetic material you can conclude the best one. Similarly, if you want to add any new material, then you are having the option like adding the material, which is the material apart from the available list in the library, and you can check the performance. The condition is same. If you want to add the new material, you should have the information in this tabular form for adding the new material. Then magnet length. So here length of the magnet we have given the input as 40 mm. Then magnet thickness. So magnet thickness is nothing but maximum thickness of the magnet. So here we have selected the magnet thickness as 9 mm. Then enter the apply button and press the OK. Okay, so accordingly pole geometry is completed. See, so here you have completed the stator part. So this is the pole. Now we'll go to the rotor. Okay, in case of the rotor, if I double click on the rotor, then it will ask for the information like stacking factor, number of slots, slot type, outer diameter, inner diameter, length, steel type, skew width. So you can go through your theoretical design and accordingly you can put the values here. Otherwise you can go through the random calculation, but it will take more time. So first of all, stacking factor. What is the meaning of stacking factor? Stacking factor of the rotor core. So here we have selected the stacking factor 0.92. Then number of slots. So number of slots of the rotor core are 12. So we have given the inputs as 12. Then slot type. Here if you double click here, then you are having the different slot designs, and accordingly as per your design requirement you can select the slot type. Like here we have selected the slot type 2. Okay, then enter the OK button. Then outer diameter. What is the meaning of outer diameter? Outer diameter of the rotor core. So here we have given the input as 55 mm. Again, in case of the unit you are having the different option, you can select as per your design input. Then inner diameter, that is inner diameter of the rotor core. Here we have given the input as input diameter is 9 mm. Then length, that is length of the rotor core. Here length of the rotor core is 40 mm. Then steel type. So for the rotor you can select the steel type. So again, as we had discussed, there is material library. You can select the different type of the material for the rotor, and if you want to add the new material, you can add the material if you are having the information as per this tabular requirement. Then enter the OK. Then skew width. What is the meaning of skew width? Skew width measured in slot number. So here we have given the input as 0. Then enter, apply, OK. Okay. So with this we have given the inputs related to the rotor. Now regarding the slot geometry, so if we enter on the slot, then it will ask either you are having the two options. You can make the auto design, otherwise you can give the input as per your design requirement. Like here HS0, what is the meaning of it? These are the slot dimensions. If you are not having the idea, then you can go through the you can just click on this slot. So here you are having the idea, or you will get the idea about each parameter. What is the meaning of each parameter? Like here HS0, HS1, HS2, BS2, BS1, BH0. So all these parameters information is shown along with the diagram of slot or the design of the slot. Okay, so that information you just input here. So HS0 is 1.2 mm, HS1 is 1 mm. All these are the slot dimensions. HS2 is 9.8 mm, BH0 3 mm, BS1 8.6 mm, and BS2 4 mm. Okay, then enter OK. See, rotor is having two main components or two main parts, like slot and winding, which is inserted under the inside the slots. So if we double click on the winding, then it will ask for the winding information. First one, winding type. So if I double click on the winding type, you can select either the lap winding or wave winding. Here we have selected the lap winding. Then multiple number. What is the meaning of multiple number? So multiple number is 1, 2 or 3 corresponding to the single, double or triple winding. So here we have selected the single winding type, that is number is 1. Then virtual slots. That means number of virtual slots per real slot. So here we have selected the number of virtual slots 1. Then conductor per slot. What is the meaning of conductor per slot? Number of conductors per slot. And if you have selected the auto design, then it is 0. But here we are giving the input as per our design requirement. That's why we have given the input like 20. Then coil pitch. What is the meaning of coil pitch? That is coil pitch measured in virtual slots. Here we have selected the coil pitch, or we have given the input of coil pitch as 5. Then number of strands. What is the meaning of this? That is number of wires per conductor. And if you select the auto design, then it will be by default 0. But here we are going to give the input. That's why we have given the input like number of strands 2. Then wire wrap, that is double side wire wrap thickness, which is 0 for auto pickup in the wire library if you are not having the theoretical design. But if you want to make the customized design, then you can give the input. Like here we have given the input as 0.09. Then wire size. See, if you double click on this, then as per your design, as per your possibility of current flowing through the winding, you can select the wire winding type or wire size. Here you are having the different options. Then wire diameter, you can select the wire diameter which are available in this list. Right now we have selected the 0.95 mm. Then if you want, then you can select the gauge of the wire, like user or auto or mixed, etc. Okay, that means you can select the wire size as per your requirement or possibility of current flowing through the winding. Then enter apply button and OK. So till now we have covered the points related to the machine, stator, pole, rotor, slot, winding, and next point is commutator. So if we double click on the commutator, it will ask for the commutator type. Now what type of the commutators are available? So for that purpose, just double click here, then you will get the idea. You can select the any one type of the commutator type among the list: cylinder and pancake. Cylinder and pancake. So right now we have selected the cylinder type and enter OK. Then commutator diameter. What is the commutator diameter? It is, we have given the input as 24 mm. Then commutator length. That is, what is the length of the commutator? We have given the input as 10 mm. Then commutator insulation. That is thickness of the insulation between two commutator bars. Here we have given the input as 0.5 mm. Then we enter the apply and then press OK. So as per your design selected or as per the inputs given by you, the machine geometry will be shown here. Machine geometry is showing here. Then shaft. If you want to select the shaft, you can select the shaft. Otherwise, you can just uncheck this box. So right now we have unchecked the box because in the last video I have given the example. Then we check the shaft option. Now see, this is the third step. That is, we have given the input to make the geometry of the motor as per our design requirement. Okay, now accordingly geometry is available. But before going to do the simulation, we want to check our design, whether that design is validated or not. And after the analysis, if there is any error, like any design input which is given from your side, if it is not within the acceptable limit, then it will show the error. Okay, it will show the error, and then you need to rectify that error. So for that purpose, what is the procedure of analysis? So just right click on the analysis and enter the add solution setup. So we have already here I have already added the setup option. Then just double click on the setup option. Then you can select you need to give the inputs related to the machine specification, like operation type is motor, load type is constant power, rated output of this motor. So right now we are going to discuss the demonstration of 75 watt meter. But if you want, you can change the motor rating. Then rated voltage. What is the rated voltage of this motor? 12 volt. If you want, you can change. Then rated speed of the motor, that is 2400 rpm. And I want to check the performance of this motor at operating temperature of 75 degrees Celsius. Okay, so you need to give the main specification, which is in general practical applications, like motor is of 500 watt or 1 kilowatt, then 48 volt or 230 volt motor. So those specifications you need to give under the setup option. Then enter OK. Now you need to analyze this machine. So for that purpose, you need to double click on the you need to right click on the analysis option and you need to enter on analyze all, so that analysis will start. So right now analysis is started and the progress will be shown here, like when this green color shows that the analysis progress, and if there is any error, then that error will be shown under this message bar. But right now for this motor there is no any error, and that's why it is showing like normal completion of the simulation on server. But if your design or the inputs which are provided from you, if there is any error, then that error will be shown here. So accordingly, whatever is the next procedure, you need to rectify that error, and then again you can analyze the machine. And at the stage here there is a normal completion of the simulation on server. That means there is no any error in the designs which are given as an input information. Now next part is validate the design. So for that purpose, here if you click on this green color, right click, then it will show the validation of design parameters, like design settings are validated, machine parameters validated, analysis setup validated, and optometrics is validated. But if there is any error, then it will be shown by red color or cross color. Like for example, for this project I have not given any inputs, and that's why if I click on this, I will select this project to understand the concept, and if I enter on the validate button, then it will show there is error in the machine parameter because we have not given the input for this project. Then analysis setup is not validated, whereas the design setting and optometrics are validated. That means make sure that before going through the results, your design should be validated. So now we'll move to our main project. That is, we have validated the design for the design setting, machine, analysis setup, and optometrics. Now what we will do, once your analysis get complete, if you right click on this, then if you right click on the setup option, then it will see, you can see that all the options are activated. Before the analysis, this performance, design sheet, curve, export, those parameters or those options will be inactive. But if your analysis get completed successfully, then those options will be active. So what we can do now, we'll go through the design sheet. So what is the design sheet? Now this is the beauty of this software, that is, before making the hardware model of this motor, we will get the detailed design sheet along with the performance parameters of this motor. So like for this design sheet, what is the information? Like general data, like rated output power of the motor is 0.075 kilowatt. That is, we have selected the 75 watt 12 volt motor. So rated voltage is 12 volt. The number of poles are 2. Given rated speed is 2400 rpm. Frictional loss 1.89352 watt. Windage loss is 0 watt. Brush displacement is 10 volt. 10. One pair brush voltage drop is 1.5 volt. Type of the load, we have selected the type of load is constant power, and the operating temperature is 75 degrees Celsius. Now regarding the rotor data, what are the design parameters? Number of rotor slots 12. Outer diameter of the rotor is 55 mm. Inner diameter of the rotor is 9 mm. Then type of rotor slots, like 2. Then rotor slot dimensions, which we have given as an input, like HS0 1.2 mm, HS1 1 mm, HS2 9.8 mm, BH0 3 mm, BS1 8.6 mm, and BS2 4 mm. Then top tooth width is 4.76 mm, bottom tooth width is 4.15 mm, 13 mm. Then skew width is 0 number of slots. Then length of the rotor for 40 mm. Stacking factor of the rotor for 0.92 mm. Type of steel, that is material as per we have selected from the material library, that is M19_24G. Then design voltage thickness is 0.23 mm. Slot insulation thickness 0.5 mm. Layer insulation thickness 0.5 mm. Then end length adjustment 0 mm. Number of virtual slots per slot 1. Number of conductors per slot 20. Type of armature winding is lap winding. Then multiplex number 1. coil pitch virtual slots, that is 5, number of wires per conductor 2, wire diameter is 0.95 mm, wire gap thickness 0.09 mm, number of parallel branches are 2, slot area is 77.42 mm square, net slot area 50.53 mm square, limited slot fill factor is 75 and slot fill factor is 85.612. Okay, now stator data. So as per the design sheet, what is the stator data? See, if we go through this list, few parameters are we have given as per the input. A few parameters are automatically calculated and those results are available here. So regarding the stator data, minimum air gap is 0.5 mm, outer diameter is 79 mm, length of the stator 100 mm, stacking factor of iron core is 1, type of steel M19_24G, pole arc offset 0 mm, pole arc radius is 28 mm, physical pole embrace is 0.726, then computed pole embrace is 0.722, then maximum thickness of magnet is 9, length of the magnet is 40 mm, and type of the magnet is HG196/96. Now permanent magnet data. So here from this all the parameters already calculated, or those are as per the simulation results. So residual flux density is 0.96, coercive force is 690, maximum energy density is 183 kg per meter cube, then relative recoil permeability is 1, demineralized flux density is 0.401 Tesla, recoil residual flux density is 0.95 mm, then recoil coercive force is 758.829 kA per meter. See, the main purpose of this RMXprt design is, of course, you will see the simulation result of the motor before making the hardware model, but apart from that, you can make your magnetic study also related to the performance of the motor, which is not possible or which is not easy, because till now if we go through the conventional study method, then we assume the magnetic flux, then magnetic flux density, etc. But here you can check the performance of this motor related to the magnetic parameters before developing the hardware model of the motor. Then in case of the design sheet regarding the commutator and brush data, type of commutator is cylinder type, commutator diameter is 24 mm, commutator length is 10 mm, commutator insulation 0.5 mm, brush width is 8 mm, brush length 8 mm, number of brush pairs are 1, then press per unit area, that is 2, then frictional coefficient 0.25, and magnetic shaft is no, because while giving the input we have unchecked that option. Another beauty is we'll get the idea about the material consumption to make the hardware model of design motor. Like for this motor, under the demonstration, what will be the parameter or what will be the material consumption we are going to make the hardware model of this motor. So armature copper density is 8900 kg per meter cube, then permanent magnet density is 7800 kg per meter cube, armature core steel density is 7650 kg per meter cube, rotor core steel density is 7650 kg per meter cube. Then armature copper weight is 0.339 kg, permanent magnet weight is 0.416 kg, armature core steel weight is 0.389 kg, stator core steel weight is 0.45 kg, and what will be the total net weight? It will be 1.60 kg. Then armature core steel consumption is 0.94 kg, stator core steel consumption is 0.45 kg. So this information will help you to estimate the cost of the motor for making the hardware model. So here you will get the idea about costing of the material which is needed to develop the hardware motor. Then no load magnetic data. So what is the information available under this? Like rotor tooth flux density is 1.75 Tesla, rotor yoke flux density is 1.75 Tesla. That means before developing the hardware model, you will get the idea about magnetic performance of the motor. Then stator yoke flux density is 2.49 Tesla, air gap flux density is 0.485 Tesla, magnetic flux density is 0.420 Tesla. Then rotor tooth ampere turns are 131.72 ampere turns. Rotor yoke pole ampere turns are 55.59. Then stator yoke ampere turns 3401. Air gap ampere turns are 3223. Magnetic ampere turns are minus 3814.9. Then armature reactive ampere turns during the starting operation are 342.29.37. Leakage flux factor is 1. Then correction factor for magnetic circuit length of the rotor yoke is 0.290. Correction factor of the magnetic circuit length of stator yoke is 0.3040. Then no load speed of the motor is 2187.97 rpm. No load current is 0.26 ampere. No load input power is 3.19 watt. Torque constant is 0.04 Newton meter per ampere. Then back end constant is 0.04572, that is kinetic energy. Then causing torque is 0.074 Newton meter. Many researchers are working on this causing torque factors also. Then full load data, that is if we check the performance of this motor under fully loaded conditions, then input current is 7.95 ampere, armature current is 3.97 ampere, armature thermal load is 15.49, specific electric load is 5.52 ampere per mm, armature current density is 2.80 ampere per mm square, friction and windage losses total, that is addition of both, is 1.60 watt, iron core loss 0.97 watt, armature copper loss 5.81 watt, then brush loss is 11.93 watt, total loss 20.32 watt, output power is 75.11 watt, input power is 95.44 watt. The efficiency of this motor 78.6993. Right now we are just discussing the demonstration, so we will not go in detail related to this efficiency, but as per your design requirement, you can go through all these technical parameters, and you are having the scope, that is in the design or geometry of the motor, you can make the changes, and accordingly you can check the performance and you can select the best parameters to improve the performance of the motor for particular application. Then rated speed is 2040.5 rpm, rated torque is 0.3515, then locked rotor torque is 5.22635 Newton meter, and locked rotor current ampere is 114.312 ampere. That means, see, you will get this information. Then commutating data, like induced voltage by inductance is 0.057 volt, induced voltage by armature reaction field is 0.11 volt, induced voltage by main field is 0.689 volt, and total induced voltage is minus 0.513 volt. Then transient FA input data, in this for armature winding, number of turns are 120, parallel branch is 2, terminal resistance is 0.091 ohm, end leakage inductance is 5.44 into 10 raised to minus 5 Henry. For one armature coil, number of turns 10, parallel branch is 1, terminal resistance 0.034 ohm, end leakage inductance is 1.81633 into 10 raised to minus 5 Henry. Then 2D equivalent values are equivalent module depth 40, equivalent stator stacking factor 2.5, then equivalent rotor stacking factor 0.92, equivalent rotor flux density 0.95 Tesla, then equivalent height of the core is 750.829 kA per m. Then estimated rotor inertial moment in kg meter square is 0.00028. So these are the parameters. But if you are interested in the particular parameter only, then you can directly go to the performance. You can select the available information or select the available options as per the information requirement from your side. Like if you are interested in the commutating data, you can select directly commutating data. Otherwise, API input data, then full load operation, metal consumption, no load operation, rotor slot, rotor winding, etc. You can select and accordingly will get the performance. Like right now the information is available for commutating data. If we select the API input data, this information is available. If we select the full load operation data, then full load operation parameters along with their values will be listed here. Then material consumption will get the total material along with their weight. In this case, if you are having the idea about cost of the material, that material in the current scenario or currently what is the cost of that material in the market, accordingly you can calculate the total cost. Then no load operation data of the motor. Then rotor slots, I am not going in detail with these parameters because already in detailed design sheet we have listed or we have discussed about those parameters, rotor slots and rotor winding. That means as per your requirement, either you can go through the particular information, otherwise in detail information available under the design sheet. So you can download this design sheet, you can just copy all this and this entire design sheet and you can paste in any Word file. Then regarding the curves, see, whenever we are going to make the hardware model, what we do, we will go through the performance curves of those motors, and if those curves are fulfilling our requirement, then only we will make the hardware model. Otherwise we need to work on the design values. So here in case of the curves, which type of the information we will get? First one is the input curve versus input current versus speed. So that graph is available here. Second graph is efficiency versus speed. So it shows the efficiency versus speed graph. Third graph is output power versus speed. So for this motor, you can go through this performance curve for output power versus speed. Then output torque versus speed. So this is the characteristic of output torque versus speed for the given input design data and the corresponding operation of the performance of the motor. Then cogging torque in 2 teeth. So this is the graph of cogging torque. Then next point is induced coil voltages at a rated speed. So it shows the induced coil voltage at a rated speed and air gap flux density. So here it is air gap flux density graph is available. So before making the hardware model, you can go through the performance curves of those motors. So this is the information. For example, suppose you are working on selection of or design and simulation of the PMDC motor for electric vehicle application. Accordingly, you can select the type of the load like constant power, and you can go through the design, theoretical design. You can give the input as per your theoretical values. Then you can check the performance. You need to go through the performance curve, and those performance curves or performance parameters, if those are fulfilling your requirement, then you can proceed further for the hardware part preparation. Okay, so we have discussed how to obtain the design sheet for the PMDC motor, how to do the simulation, and how to check the performance of this motor. But apart from that, if you want to convert this model into the Maxwell 2D design or Maxwell 3D design, then if you right click here under the setup, then there is option create Maxwell design. So here you can convert this RMXprt design into the Maxwell 2D design, or if you want to convert into the Maxwell 3D design, then that option is also available. So here you will get you can convert this RMXprt design into directly the Maxwell 2D design or Maxwell 3D design. But while making the simulation of Maxwell 2D design and Maxwell 3D design, of course you need to give the excitation for that 2D model or 3D model, and then you need to analyze that model, and then you can go through the results of that. But this video is limited or restricted for the design and simulation of PMDC motor using RMXprt tool. So that's why we are not going to discuss the additional part like conversion of this RMXprt design into the 2D or 3D model. So for that purpose, I have already uploaded one video under this channel. You can go through that channel, that is how to convert. You can go through that video for how information about how to convert existing RMXprt design into the 2D model, 3D model, then how to simulate that 2D and 3D model to get the performance curve, or to get the magnetic flux density and magnetic field strength distribution along the geometry of the motor. Okay. Apart from that, under the right click, if you right click on the setup, then it will ask to export the data. Here you can export the data. Otherwise, if you want the create the quick report, see here you will get the directly information. Like most main parameters for the quick report are nothing but current information, flux density information, percentage information, power and torque information, etc. Like suppose I have selected the torque, and if I enter on it, then the corresponding positive torque curve versus electrical degree is directly available here. So accordingly you can select the parameter, so those performance curve will be directly available under the result tab. Okay, now we'll discuss. Suppose you want to design the motor for a particular application, then what is the general steps? You need to first of all make the theoretical design, that is you need to understand the geometry of the motor. You should have the idea about all the parameters of the geometry along with their units. Then you need to work on the, apart from the geometry, you need to work on, you need to select the size of the motor, then rated voltage, that is rated power, rated speed, etc. So suppose you are going to select this motor for the electric vehicle application. First of all, you need to select the type of the vehicle, like 2-wheeler, 3-wheeler, 4-wheeler. Then you need to go through the design part for selection of the motor size for the EV application. You need to go through that calculation, and you need to select the rating of the motor, that is at what speed, then what will be the size of that motor, etc. And then you can do the simulation, and through the performance curve you can decide whether your DC motor is fulfilling the requirement for EV application or not. Okay, and accordingly, once it satisfies your design requirement, then you can make the hardware model of that motor for EV application, that is electric vehicle application. So thus we have discussed the create quick design report. Then if you right click here, then there is another one option, like export the information. So here you can export this model into the Simplorer model, and from the Simplorer, then customize design sheet, MotorCAD project, etc. So here you can convert this model into the Simplorer model, and that Simplorer model you can attach with the MATLAB software also for the checking the performance of the motor for particular application. For example, if you selected the motor and you want to check the performance of the motor for EV application, you can go through the Simplorer also. But apart from that, if you are working on the project or research work related to the design and development of drive system for particular application, so at that time drive system is not only a motor. At that time you need to work on the supply part of the motor also, like converter, controller, etc. For which you need to work on the Simplorer part. So here in this case, actually under the RMXprt tool, when we are going to check the performance of the motor, the by default simpler model is available to supply to this circuit. Okay, so here actually for this project, that converter and controller part is by default available. But if anyone wants to work on the converter and controller part, then he needs to work on the simpler part of the motor. So for that purpose, as we have discussed in the introduction video, there are different options like insert filter design item, launch EMIT, then insert simpler design. So here you can just click on this insert simpler design and you will get the idea about the drive circuit of this motor. For example, suppose if we convert this design like setup, just we right click on the setup, we'll go to the create Maxwell design and I will select the Maxwell 2D design and I will enter. Then this RMXprt design will be converted directly into the 2D model. We just will go through that. So it will take some time, and at that time here it will show the supply part of this motor also. So right now it will take to convert this model into the Maxwell 2D design. Just we wait till the time and then we'll go through the Maxwell 2D model. But to check the performance of the Maxwell 2D model or to analyze the Maxwell 2D model, at that time you need to provide the excitations. And as I have already informed in this video, I have created the separate video how to convert the RMXprt design into the Maxwell 2D model, Maxwell 3D model. You can go through that so that you will get the idea that how to check the performance of the Maxwell 2D model by using the ANSYS Maxwell RMXprt tool. So right now we are converting the RMXprt model into the Maxwell 2D model. I again request all of you, if you have not subscribed the channel, please do subscribe so that you will get the updates of latest videos uploaded under this Vidyutyog channel. So see, this is the 2D model of PMDC motor for which we have given the design inputs. So under this model, just a minute. See, whenever you are going to do the simulation of this Maxwell 2D model, then you need to select the boundaries, you need to provide the excitation, then you need to select the mesh operations, then again you need to analyze the circuit, and if there is any problem or if there is any error, you need to rectify that error, and then you will get the simulation output. So here this one, actually I want to discuss this part. See, whenever you are going to design the any motor, unless and until you work on the that motor converter and controller part, your design will not get completed. So here for this case, the supply circuit is shown here, like by the max circuit parameter. But if you want to modify this supply circuit, then you need to work on the ANSYS simpler part. So right again I revise. Whenever you may complete your theoretical design and you want to check the performance of that motor, then you need to directly, you can go to the insert RMXprt design. You can select the type of the motor like PMDC motor, and you need to give the input. You can validate your design, you can analyze your design, and you can go through the performance curves of the motor. But if you want to work on the converter and controller part, you need to work on the another tool, that is simpler. So for that purpose, either you can check the or analyze the performance of the motor in the RMXprt tool. Then you need to convert that model into the simpler, and in simpler part you can study the converter and controller part of that motor or supply part of the motor. And if you want to make your own design for supply part, then you need to work on the simpler tool. Okay, so I think this information might be helpful to you. So before going to end this session, I again request all of you to subscribe this channel to get the latest videos, and because I'm soon I will trying to upload the series of the motor, series of the simulation of the motor or different simulations by using the ANSYS Maxwell RMXprt tool. So I hope this information is helpful to you. Thank you all of you. Thank you. Take care.